Welcome. In this session, we'll look at the quotient rule. The quotient rule has no physical or geometric interpretation, so I'll simply state the rule. It says that the derivative of f over g is g times the derivative of f minus f times the derivative of g divided by g squared. There are some mnemonics supposedly to help you remember this. 1 dt goes low d high minus high d low over low low. I always want to start this off saying high d, which of course thoroughly messes it up. The commonest mistake in remembering the quotient rule is putting the sign, the negative, in the wrong place. This is why I insisted that we always write the product rule terms in the order that I gave. The quotient rule we have the same order but with a negative sign instead of the plus sign. Another way to remember where the negative sign goes is to remember that denominator has a negative exponent, so to speak. When you differentiate, the exponent comes down. So when you are differentiating the denominator, you get a negative in front from the hidden negative exponent. This actually has a deeper meaning that comes from chain rule. I will talk about it when we get to the chain rule. Now let's just look at how we use the quotient rule. This is similar to the product rule. Once you get used to it, you can write down the derivative of a fraction without having to go through all the steps. But in our first example, I will write down actually what the rule says. So the problem is to find the derivative of the fraction 1 plus x squared over 1 plus x power 4. So the numerator is 1 plus x squared, the denominator is 1 plus x power 4. So if I put this into the quotient rule, I get derivative of the numerator, that is 1 plus x squared, multiplied by, after the differentiation, the denominator 1 plus x power 4, minus the numerator 1 plus x squared, multiplied by the derivative of the denominator 1 plus x power 4, the whole thing over square of the original function's denominator, that is to say square of 1 plus x power 4. Now I just do the differentiations. Derivative of 1 plus x squared is 2x. I get times the denominator of the original function 1 plus x power 4 minus the original numerator 1 plus x squared times 4x cubed, derivative of the denominator 1 plus x power 4 over square of the original denominator, that's 1 plus x power 4 quantity squared. As I said, once you get used to this rule, you'll be able to write down the derivative, at least in the unsimplified form, as you go along. So let's do that in our next example, where I'm finding the derivative of the fraction 1 plus s minus s cubed over 1 minus s plus s squared. So the derivative is again a fraction. In the numerator, in the first term, I differentiate the numerator of the given function, which is 1 plus s minus s cubed. The derivative of that is 0 plus 1 minus 3s squared, or more simply just 1 minus 3s squared. Multiply that by the original denominator, 1 minus s plus s squared, then minus the original numerator, 1 plus s minus s cubed, times derivative of the original denominator, 1 minus s plus s squared. Derivative is 0 minus 1 plus 2s. The whole thing over square of the original denominator, that's 1 minus s plus s squared, and then squared. So again, this is the unsimplified derivative. We can prove the power rule for negative integral exponents using the quotient rule rather than more directly. So if I take x power negative n, it's 1 over x power n. Now I apply the quotient rule to differentiate this. The numerator of the fraction 1 over x power n is 1, its derivative is 0. I multiply it by the denominator x power n, then minus 1, the original numerator, times derivative of the denominator of the function I'm differentiating. The denominator is x power n, its derivative is n x power n minus 1. The whole thing over square of the original denominator, it's x power n quantity squared. The first term is 0, so I can ignore that. Then I have negative n. Then I have x to the power n minus 1 over x to the power 2n. By the rules of exponent, that's just x to the power n minus 1 minus 2n. If I combine the like terms in the exponent, n minus 2n is negative 1. So I get the derivative of x power negative n as negative n x to the power negative n minus 1. Okay. For a final example involving the quotient rule, we will find the tangent line to a rational function. Specifically, the tangent line to y equals 2x over x squared plus 1 at the point 2, 4 over 5. Except for the use of quotient rule, this is just like the tangent line problem we did in section 2 for polynomials. So I start by finding dy over dx, which I'm going to do using the quotient rule. Derivative of 2x is 2 multiplied by x squared plus 1 minus 2x times derivative of x squared plus 1, that's also 2x, over the quantity x squared plus 1 quantity squared. And then I'm going to evaluate this at the given point, which is at x equals 2. If I plug in 2 for x and then do the arithmetic, I get negative 6 over 25. So tangent line has slope negative 6 over 25. It passes through the point 2, 4 fifths. That gives me the equation of the tangent line as y minus 4 fifths equals negative 6 over 25 times x minus 2. This concludes our look at the quotient.